Today, we are talking about properties of tangents in relation to circles. Our lesson's going to be relatively quick. We have just a couple concepts to talk about, so let's get started. We take a look here at our properties of tangent sheet. What we're going to be working with today is creating tangent lines on circles. If you might not remember, a tangent line is essentially a line or a ray or a segment which comes right up and buttresses a circle. It contacts it in one individual point, which we can say is the most finite form of measurement for a circle, like 1 degrees worth or one little itty bitty tiny pieces. The tangent touches just that one little spot. And what ends up happening when a tangent contacts a circle, if you were to draw a radius out, that radius, if you will, is essentially going to be 90 degrees or perpendicular with our tangent. The point at where they contact, the term we've spoken about briefly, but it's called your point of tangency, or tangency, if you want to be fancy. But what ends up happening here when these 2 points, or these 2 lines, segments, and such make contact, we have something listed here as perpendicularity. The way that we can describe this term, and you can kind of see perpendicular in the beginning of it, is a line is only tangent if and only if it's perpendicular to the radius. So this is essentially where we can go ahead and draw some contrast and make sure that it is tangent. One way that we can account for this would be using the slope of a radius, say, in a circle, and the slope of the y equals mx plus b tangent line equation. We can compare the two of these data points and see if that information is to be true. We can also use our circle equation to see if our point of tangency is actually on the circle itself. Those are that equation with your h and k values you can see back in some of our older videos. What ends up happening if with tangent points, the only way that they work, or what we would say they're tangent segments, the pieces where it goes from, say, a shared common point out to that actual point of tangency, our AB and our AC here. What's kind of cool is that as long as they come from a shared external point, as we can call it, or a common external point, it ends up being congruent. The only way that we can connect these 2 points here is with an equal distance outside somewhere here. If we move our point A over here, we're also going to have to move it slightly closer here as well too. So it's just a nice little convenient concept. And that's really the main takeaway from this particular lesson, is these 2 ideas. Tangent lines, when they're connected to a radius, form a 90-degree angle. And in addition to that, if we have 2 tangents lines, or tangent segments, that share a common point, they end up being congruent to one another. It's the only way those physical 2 segments can coexist with one another. What I'd like to do now is show you an example of what's happening here, or like a equation that we can take a look at, an example we can look at. In this particular figure here, we have what we can call as our circle A. And with circle A, we have what I'm going to tell you is a tangent line of BD, or you can also say segment BD as well. In addition to that, we have a radius of 5 inches, and we're told that segment BD, you notice the difference in symbols there, but segment BD itself is going to be 12 inches. In our question here, what we're going to basically do is we want to solve for ED. One thing that we can take note in this particular example is that AE itself, or the portion of AD, segment AD, AE right here is going to be a radius. This little guy right here is also going to be 5 inches as well. Since they're both radii, we can say that they're essentially congruent to one another. So that's a helpful clue that you might see in a diagram or two as a little clue into solving our puzzles that get attributed to us. The other way that we can go about finding our value of ED is if we use our Pythagorean theorem. Well, you'll note, since we have a radii, since we have a tangent, we have a right angle, and we can use that equation of a squared plus b squared as equal to c squared and solve for our missing values. Question for you here, what portion of our diagram is going to be our c value though? When we set up our equation, what we're looking at is a c value which is going to be opposite our 90-degree angle. The c value is essentially our hypotenuse or our longest side. In this example, what we're going to do is just call that our unknown of x. And we're going to call it x squared, or we can just say c squared. Next thing we're going to do is just insert our values for our equation here. Our a will attribute to the smallest number, and we'll say that's going to be 5 squared. Our b value would be our medium length of 12. And of course, the 5 and 12 are interchangeable since we're just using our sum. But now we're basically just going to go ahead and solve through. We have 25 and 144 here, which combines to equal 169, which we're going to say is equal to c squared. The next thing that we're going to want to do is do a radical of 169 and a radical of c squared, so we can have a value of, say, just c, or just AD. And the square root of 169 is going to be a nice and easy 13. If we now want to go ahead and solve for our missing value of ED, or solving for ED here, we're going to take that value of 13, which represents side C or side AD, and we're going to do 13 minus our portion of AE to find EB. So if we did 13 minus 5, we get a nice, easy value of 8. So with these examples here, oftentimes you'll be able to use your Pythagorean theorem to solve for your missing side. Since we know we have a right triangle, we get to use Pythagoras' equation. Occasionally you might see examples as well. Going back a few weeks, we might be using like sine, cosine, and tangent just as a means of being able to find some of the other missing values, say if we're given things like a central angle, for instance. Next up, what we can do here is we've got our second diagram question. In our second diagram question, we're looking at circle C. We have two tangent lines. We have tangent line GF and EF. We also theoretically have our segments as well of EF and GF. We also have two radii of CE and CG. So we know these two are going to be congruent to one another. Our question here is going to be, are FE and FG tangent to the circle? One thing that we can say is for this particular question, besides just go ahead and clarifying it as an absolute yes, we can notate that because each radii, when it contacts that point of the tangent line or the presumed tangent line, we get a 90-degree angle. So for this answer, we can say yes, because course, if we're using proper grammar, it would be yes, comma, lowercase, because each is perpendicular to the radii at the point of tangency. We know these are two tangent lines because when they communicate with the radii, the way in which they communicate or work with it is at a perpendicular line. And you can show this too, just even, I might not have it 100% perfect, but we're at like at least, 89 degrees here in terms of drawing it properly. If you wanted to draw something like this, you'll just need to make a circle. The best way that you can go is pick one of your points of tangency that you'd like to use, draw just out a line from it to an arbitrary spot. Wherever you stop, then you line up your compass and drop it down like so. You'd find your point F where you'd want to start, line it down, get it close to where your point of tangency is, mark it down with your pencil, and then set up a line. And just remember that when you're going to go ahead and do that, you need to leave space for like your pencil tip because it's not directly on top of it. All right, so these are your questions for this particular section. If we're talking about tangent lines, we're talking about them being congruent to one another. If we see these perpendicular symbols popping up, if they're related to the radii, they're going to be perpendicular. In addition to that, what we also saw is that they have congruency as well too. For today, you do have another Edpuzzle video. Your other Edpuzzle video is going to be somewhat similar to this, so you may want to either go ahead and go into your independent practice packet and answer some of the questions related directly to this, or you can hold off and watch the next video because they're both very, very, very intertwined. If you have questions, drop by office hours. Let me know. Bye.